this is the introduction to Arduino workshop. So if you don't know already, Arduinos are microcontroller boards that you can build simple circuits with. I think the biggest application for them is like in simple robotics and reading sensor values. So in this workshop, we can go over 3 basic examples of the Arduino, which is the first one's going to be the hello world, just getting an LED to blink. A light switch, so this is going to demonstrate simple input output. We're going to press a button and a light's going to come on. And for the final one, the ultrasonic rangefinder, we can learn about reading sensors and displaying them on the serial monitor. So since we're doing this virtually, we're going to use a tool called Tinkercad. Usually in person, we just will have like a kit of Arduinos and you guys can play around with them. So go to tinkercad.com and make an account and then we'll get started. So did everybody make an account? Everybody get set up? Is anybody not set up on Tinkercad? I'm just gonna.
I'm set up, but where do I go to open the Arduino thing?
Oh yeah, I'll show you the guys that in a second.
Oh, okay.
So we're gonna go to circuits. So I think it kind of like looks like this. Is this the page you guys are seeing something like this in your account? All right, and then so you see 3D designs right here. You just click on circuits. Did everybody get this far? Is anybody having any problems? I can just do it again. All right, so I'm gonna assume that everybody's got this far. So now, like I said, our first application is going to be the blink. So you can just go to this site, and we're just going to copy the code and then kind of study it. So I'll paste this in the chat. Let's go there real quick. So we'll see here. There's just like it says the blink. If you scroll down, we'll show you the circuit, and we just want the code. So just kind of copy this. Then if you go to the circuits, we're going to create a new circuit. So I already have it, so I'll just open it. And we don't have to do anything. Since all Arduinos have an onboard LED, we're just gonna input code into it. We don't have to add any hardware so far. So to add an Arduino, all you have to do is on this side, if you can see components, you can search up Arduino, and then you can just like drag and drop and put them. So once everybody has an Arduino on their little Tinkercad board, we'll be able to move on to the next step. Has everybody got this step so far? Has anybody any troubles, anything? All right. So to add code, you can click here. And I think for you guys, it'll look like this at first. So all you have to do is click here and then go to text. And here we'll paste our code. The code we got from right here. And after that step, we can take a look at what the code does. So if you look at the code, there's 2 main sections in it. There's the void setup and the void loop. So the main difference between these 2 functions is void setup runs once, and it sets the pins or any global variables you're going to use in your program, while void loop runs continuously while the board is on. So we can see for this blink example, they have pin mode and pin number, and then it's an IO. So this is how, for example, on the board itself, you have a bunch of pins. And so you have to tell the board beforehand if this pin is going to be reading or outputting data. And so you use this pin mode, the number of the pin, and whether it's going to be in or out. And you only need to do this once, so that's why it's in the setup. In void loop, we want to write. So for example, in this case, we want to write to the pin that we set up, and we either write high or low. High or low means on, high, low, off. So for this case, we just want the LED to go high and then off. And then delay is how long you want it to wait. So this is measured in milliseconds. So 1 second is 1,000 milliseconds. So now if you go back here and we look at the code. So under all these comments, we see void setup, pin mode, and then the pin is the built-in LED, which I think is 13 on this board. And we're setting it as an output because we want to, it's gonna send out data, right? We want it to blink. So it's not like if we wanted a pin 13 to be a button, then we'd set it as input, but we want it as output for this example. And then in the loop, we can see that we're saying digital write, this built-in LED, and we're setting it to high. That means we're turning it on. We wait for 1 second, and then we do the same thing, but we do it low. So that means we turn it off and we wait 1 second. So what we expect this program to do is once we plug it in, give it power, it's going to turn the LED on for 1 second and then turn the LED off for 1 second. So to run this program, all you have to do is just click here, start simulation. And you should see this L, so the LED, the onboard LED should just be blinking on or off. On for 1 second, off for 1 second. So has everybody got to this point? All right. All right, sweet. Again, if you haven't gone to this point, just let me know and we can go back and make sure that everybody's on the same page. So stop that. So moving on. So this is just going over the circuit. So if we were, so for this one, we're doing the simple IO. So instead of having the Arduino just blink the LED on and off continuously, what we're going to do is we wanted to say, when I press a button, turn the LED on, and when the button is not pressed, turn it off. So this is how the circuit's going to look like. So I don't know if you guys, it's going to be easy for you guys to like put this on one side of your monitor and then copy it on the other side. I'll just open the Tinkercad for you. Maybe it'll be easier for you guys to follow. So just try to follow this breadboard design. Let me know if you guys need help figuring out the controls on Tinkercad. So to put this little like white block is called a breadboard, and what lets you kind of like hook components up together. So if you search up breadboard, you can get one, and you can just drag and drop it in. You're also going to need a resistor. Right here. And a button. Push button. And obviously the Arduino. And to make connections, what all you need to do is like click on one of the the breadboard little entry points, and then you can make a wire going to somewhere else. You can change the color if you want and all that. So I'll just leave this up here, try to follow it. And if you guys need help, just let me know. I'll give you guys some time to wire this up. So is anybody still working on it? Okay, I'm gonna assume you guys are done. If you're still working on it, just let me know. You can either put it in the chat or just unmute yourself. But as currently my chat is empty, so I'm assuming you guys are done. So just some basics of what circuit you just built. So if you don't know already, a breadboard is basically lets you make the connections without like soldering the irons and stuff. It's really good for prototyping circuits. So this is how a breadboard looks like if you take off. I think my Zoom just crashed. My bad. Let me. Anyway, so the breadboard has so these are all just pieces of metal. So, you know, as we know, metal is conductive. So if we plug in like a wire in here, like this F part, F1, we can see that everything in this like horizontal line is going to have the same connection. That's why you have the pieces of metal going this way. Then these called the power rails. If I plug in like power on these two pins, all the pins here will have that power, and that's why we have the metal, like the metal strips going this way. And that way you can easily make connections between two wires without having to like solder them or clamp them together or anything like that. You just plug them in and they're all getting the same signal power. And so as we saw here, we have some different components on the board, so we'll kind of go over them right now. The Arduino, we know what that does. The breadboard we just described, wires, just transfer electricity. And so the resistor. So a resistor is a passive circuit component that creates resistance. And they're usually made from ceramic. And the way they work is they convert current into heat. And so in most applications, you want good conductors. You want the wires to be efficient. You don't want them to make heat. But there are some applications where you do want wires with high resistance. For example, if you want to step down a voltage from hurting a component, or if you want to make like a heating element from electricity. For example, hair dryers, you plug it into the wall, so there's no like flame or anything. You're putting in electricity and you're getting heat out of it. That's done by having high resistive coils inside the hair dryer. So when you pass through current, it's creating a lot of resistance, so it's converting that current into heat. E-cigs, like vapes, they use the same thing. electronic stove stops, and foam cutters all work on the same principle of having high resistive like wires or components to create heating elements, so converting electricity, current into heat. And so the way you read, so resistance is measured in ohms, and the way you read resistors is with looking at the colors on the resistor itself. So you can see here, like the resistors they have different colors indicating their resistance. So you can just search up a resistor like color chart, and you'll be able to see. And basically how it works is that you have the first, each band represents a digit and a multiplier. So for example, we have black represents 0, brown represents 1, red represents 2, etc. And so here we can see, for example, we have brown, black, red. So 1, black, 0, and then the third band is the multiplier. So red, the multiplier is 100. So that's why, so we have 10 times 100, 1,000 ohms. So I think you guys get the idea. Are there any questions so far? All right. So moving on, this is just a quick overview of what we just talked about. So each electrical component has ratings for voltage and current. So if I have like those little LEDs and I plug them into a wall socket, it's going to pop, it's going to break. So we need to control the amount of voltage and current going to our components to ensure they don't fry. Same thing with the Arduino. If I plug in the Arduino without an adapter directly to like a wall socket, it'll just break, it'll fry. So to understand how we can use resistors to step down voltage and change current, we need to understand Ohm's law. So Ohm's law just describes the relationship between current, voltage, and resistance. If you guys have taken like physics or circuitry in college, this should be a review. If not, you don't really need to know this to make the circuit, but it's just a quick introduction. So the current is equal to the quotient, so the division of voltage and resistance. And so in this example, we're using the onboard LED, but if you were making like getting an LED outside of the Arduino, we know that the LED has a voltage of around 2.2 volts. And the Arduino pin supplies around 12 milliamps of current. So we need, if we do the math, we need a resistor with 110 ohms and somewhere in that ballpark. Usually these components have really high tolerance, especially if they're just like not LEDs, they don't do any high computing stuff. So we need a resistor at this ballpark. So now going into the software, the code of this program, of this application, we can go to this link. So again, I'll copy it and send it to you guys. So if we go here, we can scroll down. This is the circuit. And here's the code. So again, we'll just copy it. We'll paste it and then we'll study it. So it's, again, we go to code, make sure you're on text, and just paste it. Has everybody got this stuff so far? Is anybody not on this stuff? All right, so moving on. So we can look at the code real quick. Again, remember the void setup and the void loop we discussed last time and all the pin states. So here in the setup, we're setting pin mode, the LED pin to output like last time. And except we're setting it now, since we're using 2 pins, we have the pin mode button pin to input. So this time we're setting 1 to input. We want, when we press the button, we want the signal to be red. So we're setting it to input. And then button pin and LED pin are defined up here. In the loop, we're setting up a simple if statement logic. We're saying the button state is equal to the whatever this pin is reading from the button. So either high or low, on or off, true or false, like Boolean values. And then if the button state equals high, then we turn the LED on. Else, if that means it's off, it can either be on or off. We set it to low. Does this code make sense? Does anybody have any questions about this? Okay, so we'll start the simulation. And let me move this away. So now we're looking at the same LED, and if I press the button, we'll see it turns on. So the longer I hold the button while I'm holding it on, then I release off. Is everybody got it to work? Has anybody not gotten it to work? Is anybody stuck or anything? All right, sweet. So we'll stop the simulation, and then we're on to our last project. So also a quick note about using Arduino boards. You might, if we go back here, you see the Arduino, there's this big like chip, this integrated circuit. So the Arduino is really good for prototyping, but you wouldn't use it if you're making like an actual, like if you're working for a company and you want to ship stuff out, you wouldn't use an Arduino. There's a lot of like, we're just for this simple application, we're only using 2 pins. And this thing has up to 13. So we're kind of wasting a lot of stuff. We're like overkilling the whole thing. So what you can do if you want to make it cheap and like a lot of the circuits you can just get the chip up from the Arduino itself. So usually what you would do is you would use the Arduino for prototyping, figure out what you want, and once you have a final product, you burn them on those little chips. And I think, I didn't know this, but in Tinkercad you can actually get these AT-tiny chips. And so you can play around with them if you know how to like do that stuff. I'm not sure how to do it, so we don't cover it in this workshop, but just thought let you guys know. All right. So now for this final circuit, we're gonna use an ultrasonic sensor. We're gonna understand what an ultrasonic sensor does, and it's just gonna demonstrate how we can use an Arduino to sense data from the physical world. So this is the circuit we're gonna build. This one's a lot easier than the last one. You don't even need a breadboard. The directions are direct. I'll open up Tinkercad so you guys can follow it along a little bit easier. So again, you need an Arduino. You guys should know how to do that by now. Just search it up. Yeah, Arduino Uno, and then you want ultrasonic sensor. You want this one, the one that has 3 pins. There's another one that has 4 pins. Get the one that has 3 pins. It looks like this. And once you drag that in, then just hook up ground to one of these ground pins, GND, 5 volts to 5 volts. And then the signal wire, drag it to pin 7. So I'll give you guys some time to do that. All right, is anybody still working on it? All right, I can assume you guys are finished. Again, just stop me if you're still working on it. So what does this ultrasonic sensor do? So it kind of mimics the way bats, dolphins, and submarines work. Think of like radar. So I think you've all heard how bats can like see in the dark, and the way it works is echolocation. It's the same idea. So what you do is the way the sensor works, the same way like a bat, dolphin, or a submarine does it. You send a signal. Usually it's a really high pitched like noise. That's why you can't hear it, but it could be anything. It's just sound. And you wait for the echo. So I send out that signal, and then I start a timer. So and then I wait until I hear it back from the echo, since sound waves bounce off objects, and I stop the timer. And based off the speed of the sound that was going, I can calculate the distance of what was in front of me. So just a quick example. So the speed of sound in like I think at 20 degrees Celsius, yeah, it changes based off temperature. And that's why you can hear things like if you live in like a city and it gets really hot outside, you can feel like you're hearing more things because sound travels further and faster, as opposed to winter, which sounds more quieter since the temperature goes down. So we're going to assume the speed of sound is 343 meters per second, and we hear the echo after 0.5 seconds. That means we just do some math. 343 meters per second times 0.5 seconds. We know the object is 171.5 meters away. And so this way we're able to see without eyes. We can just use like ears. So we don't need any light. We can like total darkness, and that's how bats, owls, submarines, and hopefully this Arduino will do. The nice thing about the Arduino board and libraries, usually they'll handle all this kind of heavy lifting. We just have to do like this simple math. They'll do all the weird like physics of handling this. So again, we'll grab some example code and kind of study it real quick. So let me just copy this, send it. And we'll go to it. Scroll down. So this is the same circuit we built. So same thing, we'll copy. Oh. Code, go to text, and we'll paste. And then we'll start reading it. So I might zoom out a little bit. Okay, so at this point, you guys just get the idea of how it works. We're always going to have a void setup and a void loop. So here they just say which pin is going to be like the signal pin for the ultrasonic sensor. And then in the setup, they have a serial dot begin. So what the serial is it's the way the Arduino can communicate with the computer. So if this big cable right here on the simulation, usually it would be applied to your computer. And that way now you can communicate directly from your computer. This is how you like flash the programs and everything. And the Arduino can also talk back to your computer, and you can see it on a little serial monitor, which we'll see in a moment. And so this number is just the baud, the baud rate that it uses. So it's just what Arduino uses. It's 9,600. That's just the magic number. And so we're saying just begin reading the serial at this baud rate. And so in the loop, so we want this to happen continuously. We're setting the pin to output. So pins. Pin modes, because remember, we needed to be able to send a signal and then receive a signal. So this is why we need it to loop. So first it's output, and then we're gonna wait 2 seconds or 2 milliseconds and write high. So we're gonna send out that signal. And then we're gonna wait 5 milliseconds and then turn it off. So we're gonna send a signal for 5 milliseconds. And then we're gonna switch the pin mode to input. So now the pin mode 7 becomes the input pin. So now we're waiting for the echo. And and we're just writing it into this variable called duration. So now we have this part of the equation. There's my, oops, I think I lost my slides. There it is. We have this echo heard at, so we have this part of the equation. And so the speed of sound, we have to assume what it is. So if you see here in their program, they have some conversions, and I think what they do from that. Yeah, you can see that the speed of, they're assuming that the speed of sound is 340 meters per second. So they do the calculation there. And so obviously if you're using this program in like in the desert or someplace, the numbers are kind of be off. So you either have to edit this function yourself, or if you're really fancy, you could put a thermometer temperature sensor on the Arduino, and that works in this program to analyze the temperature and change the assumed speed of sound. It's called sensor calibration. Anyway, so let's run it. Stop the simulation, and to test this, you can click on the sensor. See if I click on it, and then you can kind of move this object around, and you can see that it's changing. And to check the serial monitor, where is it? I forgot where it is. It's not good. Oh boy, I totally forgot how to do this. Oh no. This. Oh man, but if you're doing this on an actual computer, you could see a little screen pops up, and it would tell you basically these numbers right here. It would tell you how far the object is on a little screen on your computer. I'm sorry, I forgot where it is. I just learned how to use this software. It's a little embarrassing. Anyway, did everybody get this part to work? All right, so somebody got it to work. Nice. On the bottom right, it shows. Is it on the code? I don't know why I can't see it, but if you guys are seeing it, that's all good. At least it works. So, so you know that you guys got all right. Sweet. And also another thing you can look at is if you see the ultrasonic sensor has some blind spots. So this is like its effective range. So if I go too close to it, I think on your serial monitor, you'll see it'll start bringing up junk value. It's too close. It's going to say like, oh, this thing's like super far away. It's not going to be able to see it. And same thing if you go outside, it'll start saying, oh, I just want to be able to see it anymore. If you go too far to the side, too far here. So just things to keep in mind if you're using this in a project. So some things you should also consider, just like some trivia about the ultrasonic sensor. Like I said, the code assumes that the speed of sound is 340 meters per second, which is true if the ambient temperature is 20 degrees Celsius. So if it was lower or higher, your readings might be off because the speed of sound changes. And another thing is the Doppler effect. So if you guys, this is kind of going into physics, but if you guys heard about the Doppler effect, it changes the frequency of the noise as you move. So if you're like cop cars, when they use the radar gun, they have to account the circuit that's in like the speed gun has to account for the Doppler effect, because since like if the cop is moving and the car in front of them is also moving, the frequency of the sound is changing. So they have to account for that as well. But you have to be going at a pretty decent speed. So unless you're making a robot or something that can go like around 40 miles per hour, it shouldn't be a problem. And also is the ultrasonic sensor, remember, works on sending like sound and hearing sound back. So this might have, this could have problems detecting all, like there are some materials that can't be detected with an ultrasonic sensor. For example, styrofoam is really good at absorbing sound. So the ultrasonic sensor is going to have a hard time because it's going to send a signal and it's not going to hear much of an echo back since styrofoam takes up the sound. Also, there's like the material they use, like, I don't know if you've seen like streamer setups or like studios, like music studios, they usually have like all these like foam pads around. They're all used to absorb sound. So if you put an ultrasonic in there, it's not going to hear any echo because that's what those materials do. They like distort the sound and you don't hear an echo. And here are some other resources to use if you guys want to continue learning about Arduino. I think these slides are also going to be posted on YouTube, so you can go back and look on it. And does anybody have any questions? If not, you're free to go. I'll stick around for a little bit to answer any questions. Thank you guys for coming.